Hi. In this lesson, I want to talk about some of the more challenging aspects of geotechnical engineering, where you need to look a little bit at slopes, but in particular, I want us to focus on tunnels, because tunneling really is at the extreme end of what an engineering geologist would be working on. Building tunnels creates a lot of geological issues, and designing the tunnels to be able to cope with whatever the geology uh, throws at you is crucial. We're also going to be looking at perhaps one of the most spectacular uh, tunneling projects, the Channel Tunnel. Although it's worth noting that in the last few years, there's been tunneling on an even bigger scale, um, building a new Crossrail project underneath London. But we're going to focus on the Channel Tunnel for this. We're working on pages 18, 19, and 20 of our Theme 13 booklets. These two diagrams uh, show the potential problems that we can have from creating slopes uh, and some of the potential solutions to these. If we look on the left, first of all, you can see that we've got uh, a whole host of problems caused by digging through rock. If you look at the road cutting first, you can see that there are a number of different issues, mostly to do with rock um, falling into uh, the cutting that's dug out. Now, if you think about road cuttings, they're they're clearly dug for a reason, usually to reduce the angle of a road. They're perhaps even more important in a railway. We see an example of a road cutting just outside Cowbridge. If you're going on the A48 from Bridgend towards Cardiff, as you go over the flyover that goes by the school, and you start going up the hill there to the Downs, you're going through a road cutting that's been dug to reduce the angle of the A48 so it doesn't slow the traffic down too much. Now you can see there we've got problems with potentially rocks falling into the cutting. There's also problems with water. If we look at a tunnel though, the problems there become even more uh, significant. We will potentially have more problems with water because we're going deeper down, so the chances are um, of going below the water table is going to be even higher. We have the problems of rocks falling into the tunnel, uh, which would be a bad thing from things like we'll call it overbreak, rock fall. We though additionally have extra problems caused by the pressure on those rocks. And obviously, the deeper you go, the more problems will be caused. So, for example, if we've got a very high competence rock, that rock could burst. It could, if you like, explode into the tunnel because you're removing the support against the pressure from one side of that rock and it's still coming from the other. If the rock has fairly low competence, like we can see in the bottom of that diagram, it might actually deform and get squeezed into the tunnel. Depending on the nature of the rock, we could even have gas building up. You know, if there's, for example, if there's coal seams nearby, you might get methane in there. So there's a whole host of different problems uh, that tunneling can cause. Now, the solutions to this, if we look at the road cutting there, we are looking at ways there either of holding back the slope, that could be building gabions, uh, it could, which are wire cages filled with rock. We have some of those by A block, holding back the slope there. A more expensive solution might be to build a retaining wall, a strong wall to hold the rocks in, or might be to pin the rocks in place using rock bolts or a rock anchor. Drains as well might be used to take water away. In tunnels, there's a number of different solutions. The old-fashioned solution was to build an arch, like a brick arch, within the tunnel and fill the space behind it. We call it grout, but it's like mortar or cement behind it. The modern solution to this is to build a concrete ring. Most modern tunnels, where they're sealed in, will be built in with this concrete ring, creating a pipe through the rock. It's a very strong shape that will exclude any of the problems with things like water or gas getting into the tunnel, and also provide good support for the rock around it. For tunnels close to the surface where the problem might just be rock falling in, we can use material called shotcrete, which is like a spray on concrete. Watch the video on tunneling to explain some of these ideas in a bit more detail. But let's look at some of these potential solutions. So for slopes, as I said, we could use gabions, like we can see in the bottom left there. You'll have seen those around school. We can bolt rock in place, so you're actually drilling into solid rock behind the loose rock, fixing a bolt, which acts a bit like a wall plug if you're putting a shelf up, to hold everything in place. Or if it's just bits of loose rock at the surface, it may just be some wire netting placed over the slope just to catch the loose bits. There are other solutions, but these are the main ones. Drainage is going to be important. Retaining walls are more of a slightly more expensive solution, but can be a lot more secure. And for tunneling, we have a whole host of different things that are used. In particular, though, modern tunnels are built on in a ring tunnel by a thing called a tunnel boring machine, a TBM. You can see a picture of one of those in the top left, and have a watch of the video there, which is, I have to admit, the only boring bit of geology. Shotcrete, as I said, is a spray on concrete. A mesh is fixed to the wall of the tunnel, and then a quick drying concrete is sprayed onto the surface to create a barrier, a seal around the edge of the tunnel. Doesn't work for it works with where there's loose rock. Doesn't work quite so well with a deep tunnel, perhaps in weaker rock. One of the most interesting geological tunneling projects in recent years was the building of the Channel Tunnel. This was done sort of in the late 1980s, early 1990s, connecting the UK with continental Europe. It made a big difference to the reliability of the connection and also the speed of the connection. The Channel Tunnel is a little bit of a misnomer, to be honest. It's actually 3 tunnels, 2 large tunnels for trains, one going in one direction, one coming the other way, and then running between the two, there's a service tunnel used for maintenance and also evacuation if there are any problems in the tunnel. And there have been problems in the tunnel in the past, trucks catching fire, for example, as a train was passing through the tunnel. With all the problems, though, or with some of these problems, the concrete ring has stood up very, very well. This is a ring tunnel, but for us, one of the most interesting things is the geology. This is a cross section through the Channel Tunnel. The vertical scale here, by the way, is massively exaggerated compared to the horizontal scale, because it reveals the features. If this was drawn actual scale, it would just look like a horizontal line. But this diagram shows us some key features of the construction of the tunnel and how they use the geology as a guide to this. You can see that the different rock units are labelled up there. Marl, by the way, is a type of clay. It's clay with calcite in it. The beds that labeled at the bottom, the Gault clay. Gault is a period of time in the Cretaceous, as is the lower green sand. It's a sandstone from the Cretaceous period. So, what I would like you to do is have a go at the questions on page 20. Can we work out how the geology of this area through the English Channel actually contributed to the construction of that channel tunnel? So, we can see that constructing tunnels is a challenging business. But if we get the geology right and pick our route carefully, then it's possible to minimize these engineering challenges and create a safe, reliable connection between two places. We'll talk about the answers to the questions on the channel next in the next lesson. I'll see you then.